So I'm going to talk a bit about how to actually program in Flink on a sort of very low-level kind of approach. So the idea is, so if you're like me, like a data scientist, and you've worked a lot with, I don't know, MATLAB back in the days, or Python now, and you start using Flink for the first time, it's a bit funny because everything is so different, right? So you don't have any matrices or anything, but instead you have these collections and these nice operations and everything. But the question is, so how do you actually keep doing the stuff you used to do? And this talk sort of is about my journey into understanding Flink better and coming from this Python background, figuring out what actually is the difference and how to do it. So if you don't have, if you already have lots of experience with Flink, right? So this might be, hopefully, you agree with me, and if not, it might be hopefully helpful for you. Okay. So normally, when you're computing programming in a language like Python, so programs look pretty normal in a way. So let's say you want to compute a sum, right? So what you do is first you have a counter, you set that to 0, and then you go over all your elements in this array A, and you just sum up the numbers, and then you return the sum. Okay? This is sort of very close to like what's programming all about. And that's so how we learn to program in these things. This is very natural. So the tools at our disposal are usually, so you have variables, so you have stuff where you can store stuff. You have a bit of control flow, like loops and ifs. And you also can have function calls as a basic piece of abstraction. So if you have a piece of code, right, you can say, actually, I can reuse this code with different values. And then you can sort of have these variables as parameters. And then that's a piece of abstraction. And then you can put together your program as part of that. So it's all pretty obvious that I'm mentioning all of this because in Flink, right, actually everything is a bit different. So now let's say, so what you usually, so I think what you are trained in if you use Python for data analysis is actually taking something like this, so taking a formula. So the first formula just computes like the sum of all elements and then divides by the number of elements, so computes the mean. Or, and then you sort of, you subtract this from all the points, sort of say, right? So this is like a classical centering operation. And you know how to take this and then put this into Python code, right? And ideally, so if you use Flink, you again have the same problem. Maybe you found some interesting algorithm somewhere and you want to implement that in Flink. So the question is, how do you go from this math to this other stuff? So for this math, right, it's also again pretty simple. So you sort of, the sum is just going over all, we already had that, just going over all the elements, summing that up. So down here, so, it actually works. So the mean is the sum of the sum divided by the length, the number of elements. And then you just subtract that from everything and return it. Right, or it can even, if you use something like SciPy or NumPy, there's even an operation which computes the mean, and then you can just subtract it. So you often, so one other thing you learn is that often you should not use for loops because it's too slow, but you should somehow pack everything into an array and then use these NumPy operations, which sort of then do the actual computation with native code. Okay? So there's already, even if you use Python, there's like going from the math formula to the code already needs some training. And in a way, Flink also requires that, but like in a different way, and that's what I want to talk about. Right, so the first thing you learn if you do use Python is that you should not use for loops, but instead you should put all your data into a matrix. And then there's like lots of operation which you could implement as for loops, but like computing the sum. But if you just call sum, then NumPy uses some C code, and then it's very fast, and you can get like performance which is very similar to what you would get if you use C. Okay. So like a very simple example, least square regression. So that's an algorithm for like fitting a line to a number of data points. And just so the main operation you have to do is compute this formula here. So where X, this large X, is a matrix, where the rows are your data points, and Y is like a long vector which computes all your labels, right? And then you just compute this, and also if you know what you're doing, right, you just know that this translates down to this operation down here, where the C is like X transpose dot, so dot is like matrix multiplication, So you set up the C sum matrix up here, and then you call numpy linalg solve to compute the equation up here. Yeah. So what you learn when you do data science with Python is you learn to break everything down into matrices, trying to break down computations in terms of matrix algebra, and also if you read the formula, you should understand that. Okay. So, and the tools you have is this basic procedural programming paradigm where you have these, right? So variables, for loops, and functions. And you also have these ordered arrays, right? These vectors and matrices, so which makes it very easy to store data. So advantage of all that is very familiar, and it's also like translating that to math is very easy. But the disadvantage of this is, of course, so the question is why are we dealing with Flink anyway, right? So everything's nice, we learned all this stuff. But the problem is, of course, that working on this level, right? So you know how to put like a formula, a bit of math into code, but it's very hard to scale. So the code which you get in the end, the computations might be very interdependent, so it's not really clear how to automatically scale. Right. So like the idea behind systems like Flink and everything is a bit different, right? So instead of taking something like a procedural language and saying, this is like how you put in math. So the approach is different. You say, so we start with operations where we know how to scale them well, and we try to collect as many of those, and then hopefully we get a system in the end where we can do all kinds of stuff. Okay, and that kind of paradigm, so I'm not sure whether that's the official name or not, but let's just call that parallel data flow for reasons which will become apparent soon. So very often you have stuff like this. So you go over some array. Yeah. So for some index sets, and then actually for each of your item in the X array, you compute something else on the Y array, right? So these are all values of X, and then you get all values of Y, but actually all these computations are independent. And this is obviously inherently easy to scale, right? So you could just distribute X on a number of machines, and then on each machine you compute, like, for that portion of X, you compute Y from X, and then you put everything together again. Okay? And there are more operations like that, but the main idea is sort of that you have this basic set X, right? Which might even be unordered to make it even simpler, right? So you have more freedom of rearranging stuff. So what other operations do we have? So we have this map. Another operation, for example, which people found is very easy to scale, is this filter operation. So you start with one set, and then for each element in the set, you see, like, is it whether some predicate holds for that, right? So you have some code which evaluates a Boolean. And that's obviously also something very easy to scale. Then there are more complex operations like a reduce operation. So in the reduce operation, you always take two elements of the set, and you compute a new element which is sort of in the same set. And then that way, so applying that to two elements, you get a new set which has one element less, right? But you can also, if the operation is sort of, doesn't matter in which order you do it, you can also parallelize that very well, because so you're sort of distributing the data, then doing the reduces on all parts of the data, and then you're putting everything together. Okay, and finally, in the end, what you have, you even have more complex stuff where you have actually key values. So this is one set, this is another set. Okay, and and the red column sort of shared. Sorry, and this yellow column is different, right? But you can have a join operation where you sort of were putting together the yellow values and the green values if they have the same key, like this. And this is again something you can do in a parallelized fashion. Okay? Yeah. And so the system like Flink actually is not like built on the ideas that you have variables and control flow and all of that, but it's more on the idea that you're always dealing with sets, and you have a rich set of operation which sort of act on these sets, and they can all be parallelized well. So if you can express something based in this language, then you automatically have an implementation of an algorithm which you can scale very easily. Okay? So the question is sort of, so before we had this procedural style where we sort of already know. So the question now is, if we have this other approach, so how do you actually program with this, and how do you sort of translate, let's say, a procedural program into this to get something which scales? Okay. So let's say, okay, and it's called like data flow, right? Because it's like you have like one set of data and you compute something and you get a new set of data, and it's called parallel data flow, or I call it because this operation can also be parallelized very well. But the general idea, so it's not like you have variables with state which you can update, but it's more like you go from one set of data, from one data set to a new data set to a new data set, and that sort of, this flow defines your computation. Okay. So so let's try, go back and do some of the stuff we did before in Python, here again with Flink. So for example, let's say you want to compute the sum of one of these sets, right? So this can, for example, be when we're doing this reduce operation. So we take two elements of x, and then we reduce those two to the sum of these two things, and we do this until we only have one element left. And then if you want to, okay, so this is easy enough. But now let's say we want to compute the mean. Okay? So this is a bit more complicated. So for the mean, we have to compute the sum, but we also have to compute all the elements in the set. And one way to do this is the following. So the first thing is we take all our elements, and then we map each element to an element which consists of this original element and the number 1. Okay? And then next what we do is we reduce all these elements sort of by doing computing the sum both on the axis and on these ones we have, right? So if we reduce all the ones, in the end we can just get the number of elements. So we take in a pair, which is like x in a counter and y in a counter, and then, right? So this dot underscore 1 is like the scalar way of extracting the first element of a tuple, and the dot underscore 2 is getting the second one, right? So we're mapping each of these pairs to a new pair where we have summed up the first entry and the second entry. And then in the end we have a set which only consists of one element, having the sum of all points and the number of points, and then in the final step we apply this map to a set which only contains one element, but then which divides like the first to the second entry, and then we get the mean. Okay, so it's already quite different from this for loop, but it's still, you can still figure this out. Okay, so Apache Flink now, as you probably all know, so it's exactly an implementation of this kind of systems. The basic building block is called a data set, right? So this unordered set of elements for some element x. And the interesting thing is, so compared to, let's say, Spark, is that for execution, actually, if you have like a string of operations, what it does is that it sets up a set of computing nodes down here, right? So this is again this reduce example. First you map x to x, comma 1, then we do the reduce, and then you do divide x by c. So, but you're not doing these steps one after another, but actually setting up all these computing nodes, and then you're streaming the data through the system. Okay. Just like a short reminder for me, so when you want to use Flink, I say just use the Scalar API. It's very nice. You can build a minimal project with Maven, SBT, or Gradle. And of course, so if you haven't done any, so this is more for the guys who have only worked with Python before. So if you ever use like a JVM type language, always use an IDE, because it does all the stuff like syntax and type checking and auto-completion. And then the only thing you have to do is to use Flink is to always import this org Apache Flink API Scala dot underscore. So you import everything from that package, and then you get going. Okay. So now let's try and rebuild this centering, right, which we had before. So we already know how to compute the sum and the mean, but for the centering idea, we first compute the mean, and then we subtract the mean from all the points. So maybe let's say it looks something like this. So we have one function which compute the mean, which is sort of what I had on the slide before. And then there's another function which says, okay, it takes this a data set. So first it computes the mean, and then it subtracts the mean from all the points. Okay? So but the problem is, so this doesn't work. So if you try to compile this, you get an error. And the reason is that this compute mean, right? So it takes a data set, and then it returns a new data set, but these operations are actually not directly executed. So they're only executed if you call an action on it, right? So if you say collect in the end, then you actually get the result or some other way to actually execute the plan. But up to there, it's all lazy. So when you say x.map, you're not actually executing something, but you're just compiling this query. So that means at this point here, when you go down, this mean is actually not actually the mean, but it's just like a placeholder for this other query which has not run yet, and the engine cannot, and that's true for all, that's also true for Spark, so you cannot run a nested query within another query. So even if you did, probably it wouldn't be the same thing, because then you would recompute this all the time, right? So the idea is, if you try to write that down in terms of these computing nodes, you can actually see, so you start with x, you compute the mean, and you again start from x, and you would want to subtract the mean from everything, right? But this is not a normal data flow, but this is somehow data which flows inside the node, not into a node, but inside a node. So this is not how it works, okay? So that's what I said. So variables only hold lazy computations, and you cannot actually nest these elements. Okay. So what can you do, right? And so the maybe it's not that clear, but the main difference we see at this point is, like, if you're in Python, you can just do parts of your computation, collect the results in variables, and then put everything together in the end. But if you use something like Flink, it's not that easy. So unless, I mean, of course you can always do like very small queries, but Flink, like the real power of Flink only comes when you combine everything and you have very long queries, right? So then Flink can really optimize and you have a good throughput and everything. So there are two ways you can do this. So one is you can actually do like a cross join. So cross join actually is if you have two sets, then this is a resulting set which contains all the possible combination between the two sets. But we are using this on result sets which have only one element, right? So if both have only one element, then the new set also has just one element. Or if you sort of combine an element which has one set with another set, then it doesn't grow larger, right? And the other thing is broadcast variables. So if you do the cross join, how does it work? So the mean is still the same thing, okay? But in the centering now, what we do is we again compute the mean, but now we've learned that this is actually not like the mean of the data points, but it's the data set which sort of holds the computation. So what we do is we have the original set, and then we cross with the mean here with a function called cross with. So cross with tiny is a special optimized version of cross, which knows that the second set is very small, right? So it tries to not sort of run a full join, but something more efficient. And now if you do this cross here, what you do is that sort of for each element of x, right? So you're actually putting the mean value next to it, and then in the next step, in the final step, you can do this mapping here. So if you write this down in the nodes, like representation, so you start here, you compute the mean, but then actually you get like the x's and the mean into the join operation, and then you have like a combination of all the x's and the means, and then you can do the subtraction and you get out. So this works, right? So this is one way of getting all these data together into one to continue the computation. But it seems sort of excessive because first sort of we're copying each mean value to all elements of x, and then we do this. So it would be nice if there's an easier way where we're actually not copying the data first, and then if we just sort of have it there and can apply it. Okay, and that works through broadcast variables. So the original idea with broadcast variables is that you somehow can send signed information to the worker nodes, and then it's only copied once to each worker node, right, and not duplicated everywhere. But this is now a thing specific to Flink. So the broadcast variables are data sets actually. Okay? Right, so it could be some data, but it can also be a data set. And if it is a data set, then within the map operation, you can access it as a Java collection. So it gets unpacked from this data set. You can actually just get a list where you can actually touch the values. And this is also different from, so in Spark, it's also different. In Spark, you can only broadcast variables which are already computed computations. So what this means, sort of, is, okay, the only problem with broadcast variables is that if you want to use them, right? It's not so easy to access them, but actually you have to sort of extend this rich map function up here, and then define this open, override this open method, which gets the configuration, and then you can, from the runtime context, you can sort of extract the broadcast variable and you can put it somewhere. So this is done only once, and then you have that stuff available down here, right? Okay, and the idea is, of course, that you don't do this like every time you want to do a map. Instead of this nice like inline function notation, you have to write this, but that you sort of have a helper class which lets you do this. Okay, and actually, so in the Flink ML library, there's just a thing like that, and it's called map with broadcast variable. So you're doing sort of a map down here, but you're also putting in this broadcast variable. Okay, and so now what happens if you look at the notation down here? So you start with the x, you compute the mean, and you have this other thing here. But this actually gets put as a broadcast variable into this thing down here, which means that sort of as soon as the data is available, it gets stored in the node, and then you can access from there as if it's like a normal Java collection. Right? And so this is actually the way this works. Right? So what we have sort of is in like a sort of little code pattern. So normally you would do something like, so you compute x, you compute y, you compute z based on x, and then you get a result based on y and z. So this is like what typical programs often look like. But in Flink, you sort of have to put that together. So you do some data set computation and get a data set, right? But not really. So this is just the query which is set up. And then you do it again with some other computation, and then you are using these broadcast variables sort of to tie in the results you have into the data sets. Okay, so it's a bit messy, but actually I think if you, the first time you see it, but if you understand why this has to be done like this, then it's again a pretty mechanic point. And as I said before, so even with Python, if you think, oh, Python, I just can, look at the formula, just type it down. So in Python, you also often have to do a lot of translation to get it into this matrix format. So I think it's not as bad. Okay. So the other thing, so this is one thing. The other thing which is sort of odd is that we don't have any ordered sets anymore. So in Python, right, so this procedural stuff is one part of the tools you have. The other tool is that you have these NumPy arrays. So you always have these arrays and they are ordered, right? So this sounds like a pretty trivial thing, but the way this is often used is that you have like different arrays. And actually, these are like different attributes of something you're looking at, like a data point, okay? And the index sort of ties in together all these information. So for example, if you're trying to have some features x and you want to predict something, some value y, right? Then, so like the ith entry here, x, these are the features which corresponds to the ith entry in y, right? So it's so natural that you don't have to think about this anymore. But what happens if we don't have that anymore? So if I take away this orderedness, right, then we cannot just have one set x and one set y, and we sort of know what corresponds to what. But instead, what we have to do is actually to have instead a data set which consists of pairs of x and y. So these two things have to be coupled explicitly, right? And that's actually the way it's often done. So you have a type like labeled point or so, which you can use to represent this kind of stuff. Okay. But what if we don't have these arrays, so how do we actually represent matrices inside our data set? Right, so we now know sort of how to deal with these intermediate results and all of that, how to put that stuff together, but how do we, so if I don't have a matrix which is sort of ordered, so how do I do it? And actually, so there's one way to do it in a very explicit fashion, and this is to encode, to sort of, so we have this vector here, and what we need to do is we need to encode, we need to store this vector to represent it inside of Flink as an unordered set, right? And one way to do it is just to put the index in here, so then you actually know like which part here belongs to what. But then if you want to do addition, right, then you first have to join A and B based on the indices, so that you're actually bringing together the corresponding entries. And then in the map, sort of, you have, so _1, this would be the index for the value of A, and then, which is the same as the index for the value of B, and then you can actually add together the two parts, and then after that, right, and then you get the result. So after the join, what you have actually is like something like this. So it's a set of entries, and it's like pairs of pairs, and in the pairs you always have like the index and the value, and the index is always the same between all the points. Okay? So this is like the most straightforward way to represent matrices, but of course, right, so the question is how fast is this? If you always have to do this join, if you always have to artificially align these points before you can do the computation, that doesn't seem right. Okay, but very often, as it turns out, so what you have to learn sort of is to look for certain patterns where actually you have a computation which involves matrices, but which is not dependent on the order. And one of these examples, for example, is a sum, right? If you have a sum, so you have these, so in the computation of least square regression, if you don't remember, you have to compute this matrix here. And this matrix can be computed in many different ways, but one way to represent is to actually say it's just a sum, and these are the feature vectors, and you have like an outer product of these 2 points. And then X transpose Y also can be written like this. So you can write it in a different way, right? And then it gets very difficult to do it, but if you write it like this, it's just a sum. And sum can be represented by reduce operations because it doesn't depend on the order, right? So you can actually rewrite the least square regression which we had before by just doing like by first mapping each point to this outer product and then computing the sum with the reduce and mapping each X and Y to this product here. So so Y is just a number, X is a vector, and then reducing it down this operation, right? And so what I try to say is that, so in principle, if you want to represent matrices, you lose all the ordering, and you might have to put explicit indices down here, just like this. But sometimes you're lucky, and actually you don't actually have to know like the ordering because you're just computing a sum, right? So and then here, of course, so first you do this, then you get a data set which contains like the first part of the equation, data set which contains the second part of the equation, and then as we've learned, so you put this together with this broadcast variables, so you extract the information down here, and then you can just do like a normal, solve the equation in a normal way, and then you get a result, right? And the nice thing about this is, as I said, so this does not really scale to many features because you have this like solving this linear equation here, which has as many dimensions as features, but it would scale to like any number of data points. So if you have it like this, these sums, I don't know if you have 10 million data points, 100 million, you can just scale it out, and then at least this part of the computation becomes fast. Okay, so this was just like a very first introduction. But I think like the basic thing to understand is, so on the one side, normally what we're doing, right, without actually thinking about this, is more this procedural kind of stuff where you have variables, control flow, and functions. And on the other, but this doesn't really scale. But on the other hand, here, if you have something like data flow, right? The basic building blocks. So it's much more in terms of you have one data set which is somehow unordered, and you apply something, you transform this into a new data set, and so on. And these can sort of be scaled well, but they cannot be nested. So this kind of like function call doesn't really exist there. And then, especially in Flink, one nice way in which to sort of, you have to combine intermediate results using broadcast variables. So there's more in Flink. So there's support for iterations, right? So if you very often in like data analysis algorithms, you're actually computing an approximation to something. So you're iterating. You can do that as well, which is very nice. And then, so the last sort of caution is, so in Scala, if you call a function, you can have this implicit information, right? And then the compiler at that point sort of assumes that it's somewhere defined. I'm just saying you should just be beware of these type information implicit. So once you start using these, oh well, okay. So once you start using this, just remember that you heard it here. Okay, so that's it. Thank you very much. Any questions? Yes. I think there was a guy with a microphone somewhere. Yeah.
Hey, Mikio.
Hey.
So my question is, you mentioned that in Spark we have the broadcast variables are actually local variables that are in the driver. Yes, but here in Flink we use the broadcast variables which are actually in datasets. So maybe you can talk a bit about what are the trade-offs between the two approaches and how they work when you're trying to actually program, let's say, machine learning programs. Which one do you feel works best? What I think, what is better for? Which the paradigm do you think is better fitted to machine learning, and what are the reasons?
Yeah. So so the problem in Spark is sort of you always if you want to broadcast something, you first have to collect it back into the driver, right? So that might be, and that means it cannot be too much data, so it's not scalable in that fashion. So here, on the other hand, in a way, it also gets loaded into the computing node when you start this thing. So yeah, it's very similar. So the only thing is that you because you have the streaming kind of approach in Flink, you have you can wait for the computation to finish, right? So in Spark, you have to wait until the data is there, and then you can broadcast it. But here, it's more like it's actually more. So the latency is probably lower. Yeah.
So do you have experience with Spark also, or only Flink? Because Spark mlib, you have RDDs of dense vectors and sparse vectors, and you can do, as long as it's an RDD, you can do all operations in them with no restriction. It seems. Yeah. I found it very easy to program with it.
Yes. Yeah.
Actually.
Yeah. No, so in Spark, this is the idea is a bit different, that you have these small.
So that's why I'm asking about comparison.
Yeah.
Exactly.
Right. So, but then
So, for example, the example that you in the beginning, as long as you cannot nest RDDs, but as long as you don't nest them, it works.
Yeah.
So, and you can. Yeah. So. And as long as you have an RDD of dense vectors, on the dense vectors you cannot use RDDs, but you can use the library of NumPy for.
Yeah.
So.
Yeah. Okay.
Yeah. Just. You want to reply?
Oh, sorry. No. So I think in that respect, Spark is a bit easier to use, right? Because it can just do something, but you always get the result back into the driver. Right, and so Flink, then the idea is more a bit that you can construct longer stuff, and then you don't have to wait for all the stages to be finished, but you have a higher throughput and less latency. Yeah.
So so I'm a data scientist, whatever that means these days, and so your example of just adding vectors, something that in our world has to be smooth, is hella clunky. How do you anticipate that being smoothed out? If, for instance, this infrastructure is ever going to be data science friendly? Because it seems from this example alone, it's kind of like you're kind of shit out of luck if you want something smooth to do the basics and the less trivial.
Yeah.
How do you anticipate? Do you anticipate this being a pothole in the road that gets covered up and eventually eased over, or is this always going to be something you think that will be a part of this paradigm?
No, I think it's, so you're asking whether it's going to be in the end, as easy to use as this other stuff?
Yeah. Will we converge to something?
Yeah, I think so, yeah. I definitely think so. I think there's I haven't talked about this, but those Spark and Flink both, they also now have Python interfaces, which make it easier to integrate with that stuff. I think just working with matrices is always So these things really get nice, like in the talk before. So when you have the full pipeline, you start with some text files, you do all the parsing, extracting, and all of that, right? And then sort of having that already scalable, and then in the end, you sort of like the actual machine learning kind of stuff might be a bit tricky. But so I think the what do you say so the value which you get from this is also that it's much more integrated across, like from the beginning to the end, and that it's also all scalable, like especially the easier parts. Yeah.
Wait, sorry, one last follow-up. But I thought the Python API was only for 1/2 of the Flink. So there's Flink data stream, and then there's basically there's data star, 2 chunks. There's a Python API for one, but not for the other. Right? And so
might be right now, but I think like in the future. So I think my opinion is sort of that if you really want to use this, you should use Scala also for performance reason, because this Python is always like going back and forth between like the JVM and the Python interpreter. But yeah, so my experience, so it's definitely, I think they definitely realized that this is very important for data science, so they will work hard on making this more usable, I think. Yeah.
Just a small comment. In the program that you had in the beginning, in Spark reduces an action and not a transformation, which would mean it will work. You see?
Yes.
Just want where map is a transformation, but reduces an action.
Yeah.
I would like to answer the question that was asked about R-like syntax and making it friendly, R-friendly. And we are integrating Flink with Mahout, and Mahout is having a distributed linear algebra providing R syntax constructs. And Flink is part of the integration. It's coming. We have a PR right now. So we'll be using the stuff that you have presented today with an R syntax wrapper on top of that. So that's going to be friendly for all the data scientists, and they won't miss out on the R syntax. Sorry? Samsara, yeah. And if you have been to Sebastian's talk yesterday about that, that's pretty much what it's all about.
Okay, thanks for the talk. You mentioned SkyPy, and SkyPy has several implementations of sparse data structures, which you know essentially implemented yourself. If you think of the sum example, that scales, for example, and your calculation of x times x transposed used a dense vector structure, which wouldn't scale for high dimensional features. Do you know of any plans to offer some linear algebra abstractions for Flink, and especially for sparse data structures?
Yeah, I think this is all very much work in progress right now, right? But there's stuff like that. Not sure, yeah. So you probably know better about this.
Come on.
Yeah, in FlinkML we have a vector abstraction that has dense vector and sparse vector implementations already, and they are currently backed up by I think the Scala NLP library. So for forgetting the name now, excuse me. Yes. So they're currently backed by Breeze, but Till has coded them in such a way that that is, I think, easy to change out. Yeah, that is true. But if you use a sparse structure, then that vector can also become quite large.
Okay. Yeah. So I guess then it's time for coffee. Thank you very much.